In a binomial experiment, the probability of getting exactly x successes in n trials will be given by the formula below. It involves p, the probability of success, q, the probability of failure, and also a combination where we do n choose x. Now that'll be the theoretical probability of exactly x successes. But in the real world, when we actually perform the experiment, we'll get empirical probabilities. And so that's what we're going to do here is we're going to actually perform an experiment involving coins. The experiment is this. You flip the coin 4 times and record the number of heads that occur in 4 flips with a single tally mark in the table below. So instead of doing it on the desk, I'm actually going to use an online simulator of coin tosses. It samples atmospheric noise, so the results should be effectively random, just like flipping real coins. So all I have to do is select the number of coins that I want to flip. It's called random.org. And let's see the results we get. Okay, I got 1 heads out of 4 flips. So let's go ahead and put a tally mark here because the X now represents the number of successes that we get in 4 flips. I'll go back and we'll just flip again. Okay, this time we've got 3 successes. So we want to put a tally mark here. And that's how it goes. We want to actually repeat this experiment 10 times so that we get a good sample size here. Okay, 2 successes. 1 success. 3 successes. 4, okay. 2. Okay. Okay, that's 10. All right, now we can calculate the empirical probabilities of these different results simply by dividing our frequency by the number of experiments that we performed. We did it 10 times, so we'll get 0 out of 10 for no successes. I didn't get 4 tails in a row. Let's see, we do have 5 out of 10 here, which will be 0.5. We got 2 out of 10, which makes 0.2. 2 out of 10 again. And 0.1. Okay, I'm going to graph my empirical probabilities on the left, just using a bar of width 1. And then we'll give it a height. I think I can probably count 1, 2, 3. Yeah, I'm going to have to count by 0.1s here for my probabilities. Okay. Okay, that's the bar graph I get. And that's our empirical results. Now, what we'd really like to do is let's find out what the theoretical results should be. Keep in mind that this would be if we were to perform the experiment not just 10 times, but an infinite number of times. An infinite number of times, then what probabilities do we expect to see for 0 successes, 1, 2, 3, and 4 successes? That's what we'll use this formula for. So the n refers to the number of trials that you perform. You have to use combination. X for this top row will be 0, so 0 successes. Now you have to put in the probability of success and raise it to the x. And it's a 0 because in this case we want to see what the chances of us getting no successes. And then how many failures. We want n minus x, which in this case would actually be 4. We just want to do that on calculator. You can punch it right in to either the Ti30X2S or the Ti84. I get 0.0625. Okay. Now, how does that look on the Ti30 calculator? It should look like this. You want 4 NCR 0, 0.5 to the 0, 0.5 to the 4. That would be fine. You can just leave it like that. That will work well. Okay. For the next one, we'll want 4 choose 1, 1/2 to the 1, 1/2 to the n minus x, which is actually 3 here. So I'll just go back and change your numbers. Now we get 0.25. Okay. Four choose 2, 1/2 to the 2, 1/2 to the 2, 0.375. Okay, then we'll have 4 choose 3, 1/2 to the 3, 1/2 to the 1, 0.25. I'll try to clean that up a little. Okay. And then 4 choose 4 1/2 to the 4 1/2 to the 0. Clearly there's a symmetry here. Okay. Now let's plot the theoretical probabilities. Okay. So they don't really look the same here, do they? It's possible that we just randomly got an unusual sample. Sometimes that happens. It's actually expected, especially when you have a low number of trials, like 10. So what would we expect to see happen to the empirical probabilities if we were to perform the experiment more times? Well, what should happen over time is that the empirical probabilities would be expected to approach the theoretical probabilities and the empirical graph should move closer to the theoretical graph. Right now, they don't look all that alike, but as time goes on, as we do the experiment more and more times, we expect that eventually it will. All right, next, we're going to want to find the experimental mean for our 4 flips of a coin. And so one of the methods that we have for doing that is just to take our probabilities, 0.5, 0.2, 0.2, and 0.1, and 0. We just want to multiply those by the x. All we're doing there is using the formula, well, let's call it experimental mean equals the sum of x p of x is p hat, because this is it's experimental, it's empirical. So 0 times 0 plus 1 times 0.5 plus 2 times 0.2 plus 3 times 0.2 plus 4 times 0.1. Those were our empirical results. That'll help us find an experimental mean. It's 1.9. Let's plot that on the distribution graph up here. .9 occurs right about here. That's the experimental mean. But now we want to find the theoretical mean. And that has its own formula. Mu equals NP. Notice it uses P, not P hat, because P is the true probability of success. We flipped the coin 4 times with a true theoretical probability of success of 1/2. So the actual mean is expected to be 2. Let's go ahead and sketch that in. So for some reason, when I flipped it, we had a lot of 1s, which doesn't always happen. The theoretical mean is 2. The experimental mean is 1.9. Pretty close. Now can we calculate the experimental standard deviation for our flips of the coin? Easiest way to do it is just use the formula square root of the sum of x squared p of x minus mu squared. So our x squared p of x values were 0 squared times 0 plus 1 squared times 0.5 plus 2 squared times 0.2 plus 3 squared times 0.2 plus 4 squared times 0.1. Then I want to subtract my mean squared. Just take a square root of all that. Okay? So I get 1.044. Keep in mind this is experimental though. Not theoretical. Okay. Now let's find the theoretical standard deviation using its formula. That's on the right here. It is sigma equals the square root of n times p times q. That's for binomial experiments. Our n is 4, our p is a half, and our q is a half. So it's actually 1. So wow, I mean, our experimental mean was pretty close to the theoretical mean, and our experimental standard deviation was pretty close to the true standard deviation too. What changes would we expect to observe if we performed the experiment more than 10 times and kept cumulative empirical results on that? We expect that the experimental mean would move closer to the theoretical mean, mu. The experimental standard deviation would be expected to move toward sigma. Now we don't know for sure that it will, okay? But that is the expectation according to the law of large numbers.